Hello everyone. In this video we are going to talk about Model Reference Adaptive Control or MRAC for higher order LTI systems, linear systems, where full state feedback is possible. So you can get feedback from all of the states. So in the previous videos, if you have watched me, I've gone through first order systems, both linear and nonlinear, and now this is time to basically go to higher order systems of arbitrary order n in this case, where the ODE governing the system is given by equation 1, an nth derivative of y with respect to time plus all the way to a naught times y equals u, where u is the input of the system. So the transfer function, if you want to write it, y over u is basically 1 over a n times s to the n plus a n minus 1 s to the n minus 1 all the way to what? To a naught. Okay? So it's a polynomial, it's a ratio where 1 is the numerator and nth order polynomial in the denominator. And the model that you want the system to follow is very similar, nth order polynomial again on the left side, and again the order is n, the input is this reference input r, and the coefficients of that system are alpha instead of a. Now, in order to control this system, so the goal is that, again, y converges to what? Ym, or the error, which is the difference between these two, that will converge to 0, okay? So you need to pick a control signal u to make it happen, and the signal that we choose, u, is equal to an times the signal z, which I'll explain it in a second, plus all the way the rest of all of these terms. So the rest of the terms in u are exactly the same as what? The terms on the left-hand side of the governing ODE, and the goal here is all of these terms get canceled. The only term that you add is an times z. What is z? Z is the signal defined by equation 3, which is ym to the n, nth derivative of the model, minus beta n minus 1 e to the n minus 1 all the way minus beta naught e, where e is the tracking error, ym is the output of the model, and these betas, they form the polynomial like p to the n plus beta n p to the n minus 1 all the way plus beta naught, which is what we call a Hurwitz or stable polynomial. What does it mean? It means if you solve for this polynomial and find all of the roots p1 all the way to n, all of these roots are what? Stable. What does it mean? It means the real portion of these roots is going to be negative. Okay, so the system is stable. And if you want to look at Hurwitz stability criterion, there is a video under my playlist controls when I taught linear controls in it. You can see that you form the table and then arrange the coefficients of odd terms and even terms of power of p and form the Hurwitz table, Routh-Hurwitz method, and you determine whether all the roots are stable or not, which means they are on the left side of the imaginary plane. So these betas should be picked such that the resulting polynomial, which is this, is a Hurwitz polynomial, or it has roots on the left side of the imaginary axis. If we pick that z signal based on 3 and plug it right here into the control signal 4, I can show you that if you plug in this 4 into 1 using 3, it should give you the same y as ym over time, and I'm going to prove it to you. But first thing I want to say is this u that you see here, an times z all the way to a naught times y, we can also write it as a product between a vector parameter, or parameter vector, sorry, a, where a has all of these parameters in it, an minus 1 all the way to a naught, and v is a variable term which is involving what? Z and then yn minus 1 all the way to y dot and y. So the first portion is the time variable portion. The second portion is the unknown parameters in general, okay? And so we say the equation of motion for this system is linear in parameters, which I have explained in one of my other videos. What does it mean when we say the equations of motion are linear in parameters? That's the meaning. So first, before I say that these parameter A's of the system are unknown, for a moment, let's say they are known. Why do we do that? Because we want to make sure picking control law 4 along with 3 will guarantee me zero convergence error. Error convergence to 0. Is that right? We have to first check. When you pick a control law, you have to show that it is working. So what do? We are going to plug in 4 into 1. If you do that, the left-hand side is equal to the right-hand side, which is u now. Okay? Yeah? If you call this result 7 and then plug in 3 into 7 for z, for this z, if you plug in that, then you're going to get what? Let me show you. First thing is, all of these other terms would get canceled. And if an is not 0, which in this case it shouldn't be, that get canceled from both sides. So what you will get is the nth derivative of y is equal to z, this part. But what is z itself? Now it's time to plug in the relation from 3, so it's ym nth derivative minus all of these beta terms. And now, if you bring all of these terms to the left-hand side, y nth derivative minus ym nth derivative becomes e to the nth derivative of error, and then all of the other beta terms are going to be added, and you get equation 8, which is your aerodynamics equation. And if all of this beta selected, that's polynomial, that we said is a stable polynomial, then there is guarantee that e should go to 0. That's why we pick those beta that way. Because if you look at equation 8, that's the same as this equation. Okay, this equation is the characteristic equation of equation 8. So if the roots of that are stable, then that means e should go to 0 because they all have negative real parts. So clearly see that picking 4 for control law along with definition of z based on 3 would definitely give you error convergence to 0. So it's working. Now the problem is these parameters ak, a from 1 to n, these parameters are not known. And actually it's not k1 to n, it's k0 to n. So let me modify that to make it right. It's from 0 to n, okay? Because you have from a naught, as you can see, all the way to an. Now, let's say we don't know these parameters. Now what? What would you pick for control signal? The answer is the exact same thing as last time, except these a coefficients that I had in equation 4, now they're going to be replaced by a hat. Why? Because these are the estimates we have from these a's. So my u can be written as the v times vector a hat, okay? And the z that I have in v, this z is again exactly coming from equation what? 3. So equation 3 is not going to be touched. Equation 3 is still going to be used for definition of z. The only thing is the control law, instead of being 4, now it is what? Now it is going to be 9 instead. Okay, where the a's are replaced with a hats. That's all it is. Okay, now that we have it, and we know that if my a hats converge to actual a's, that control law is going to work. So the question is, how would you change the a hats? These a hats, they are variable. How would you change them versus time? Okay, what is your adaptation law? So we're going to discuss that. But First, if I plug in this equation 9 and 3 back into 1, your aerodynamics equation now becomes this equation 10, where you can see that the coefficient an times all of these derivatives of error and the error equals v transpose times a tilde. What is a tilde? That's the difference between estimated parameters and actual parameters. So clearly, if this a tilde can go to 0, then this right-hand side is 0, and because the way we chose beta, that means error can also go to 0. Okay, so now what do we pick for this convergence? And the answer is what? The first thing you do, you write this aerodynamic equation 10, you write it in the state space format by picking the state vector x equals x1 is e, x2 is e dot, all the way to xn is the n-1 derivative of e. If you pick your states like that, then clearly x1 dot becomes x2 and x2 dot becomes x3 all the way to xn dot, which is basically equals to the nth derivative of e. Now this is what, if you look here, that is clearly equal to the right hand side, which is v transpose a tilde divided by an, right? So you divide both sides by an, and then because you only want this, you have to take all of these other terms to the other side too. Yes, so it's going to be negative beta n-1 en-1, which itself is xn. So it's going to be negative beta n-1 xn, negative beta n-2 xn-1, all the way to what? To finally, as you can see, basically negative beta e, and e itself is x1. Like this. Okay, so these are your state space equations. And now we want to write it in a matrix format. So if you write it, your A matrix, if you write it this way, x dot equals ax plus b times the right-hand side, then A matrix is going to be this. The B matrix, since only the right-hand side is affecting the last derivative, then it only will have a 1 here. The output of the system, y is equal to e. So the output of the system, I want it to be e, which is the same as x1. So your C matrix will only have a 1 in the beginning, nothing else. And clearly there is no d here, d is 0. And the right-hand side, which is the input of the system, is going to be this guy. This is the input of the system. So this is like your new u, if I call it u prime or something. And E, which is the same as the output of this system, is going to be C times X, where X is this vector here, and C is that matrix. So here we wrote our aerodynamics equations into state space format. If we write it this way, then I can claim that this following adaptation law number 12, is going to make the system converge to 0, the errors. What is this adaptation law? It says a dot, a hat dot, which is the change of these estimated parameters versus time, is negative. Gamma, this gamma plays the same role that we had in the first, if you remember, let me show you, when we had the first order systems. If you look at them, we had this gamma, this gain, this constant positive gain, because the system was order 1. But now that you have n plus 1 parameters of A, this has to be a matrix instead of a single number. So this capital gamma is an n plus 1 by n plus 1 symmetric positive definite matrix, which, if you remember, we call it the adaptation gain matrix. The bigger the absolute value of the components, that means the faster your errors will converge to 0. This V here is the same V that we had above. That's this same V in relation 5. then B is this B matrix here, this X is this X here, and this P here is another symmetric positive definite matrix that you can find by solving this equation number 13, which we call Lyapunov equation. Here, A in this Lyapunov equation, A is the A matrix of the system, P is the solution that you need to find and plug it into 12, and Q here is again an arbitrary, remember, an arbitrary symmetric positive definite what? Matrix. Okay? Yeah? So negative Q. And in MATLAB there is this command lyop, and you can give it A and Q, but the equation that it solves is different than this. Okay, if I show you what lyop does in MATLAB, so you have to be a little bit careful about it, because it does not exactly give you this, okay? So I want you to pay attention when you hear determine a Q and you have A and you want to find P. If you look at the equation it solves, the equation is this. AX plus XA transpose equals negative Q, right? AX plus XA transpose. Okay, look again. XA transpose. X is the same as P for us. Now, if you look, clearly you see the order is reversed here. And the same here too. The order is reversed. Here, P is multiplied from left to A, and on the other side, from the right side to A transpose. Here, it's exactly backwards. So pay attention that when you use the lyop, what you will get. Okay, the X that you will get might not exactly be the same as this P. And we're going to check it with you with an example, whether you can trust this lyop solution or not. But once you solve for it, you go with this arbitrary Q and you have A and you find P, you plug P in this equation 12, and that gives you the time derivative of these parameters, which if you integrate it in Simulink with 1 over S block, then the answer is what? Going to be A hat. And once you have A hat, guess what? Once you have A hat, you're going to plug it into your control law. Since you have V, you multiply by A hat and you get U to pass on to the system to control it. Now, how would you know this is going to converge? So the Lyapunov candidate function that I want you to try is this one, V equals X transpose PX. They have to be bold font. Plus A tilde transpose gamma inverse A tilde. Clearly, this matrix is going to be, this function, sorry, is going to be positive. And if you take derivative of that, you can find that the derivative is what? Is going to be V dot equals negative X transpose QX. And I'm not going to prove it for you here, but you can do it as a practice yourself, right? Knowing that here you have basically this part. When you take time derivative, the term that has derivative is X. P is constant, really. Okay, so you can get the derivative of this term here. Gamma inverse is constant, so the only term that has derivative is A tilde. And the derivative time of A tilde and the derivative time of X. So if you get here basically X dot, so you know here you're going to get what? You're going to get 2P times X dot. And for this term, you're going to get 2 gamma inverse times A tilde dot. And for X dot, you're going to replace it by this. Okay? And for A tilde dot, you take a derivative out of equation 10. If you take a derivative out of equation 10, you get A tilde dot to be a hat dot minus A dot, but A's are constant, so it's just this. And A hat dot is this relation 12. Okay, so this is the same as a hat dot, which is equation 12, and this x dot is basically this equation 11. If you plug in and simplify, you should show that v dot is going to be what? Negative x transpose qx, which is clearly negative, so you definitely will have a what? A stable system. And you can see that the Lyapunov function is picked of two parts. The first part is the tracking error, and the second part is the error of the parameter estimation. Because x, if you remember, x is e and all of its derivatives. So when x goes to 0, that means e and all its derivatives goes to 0. When a tilde goes to 0, that means a hat is converging to a. So clearly, equation 12, where it gets b from 13, it gets b and x from 11, gamma you just pick, and it gets v from relation 5. That should definitely stabilize the system for you. Okay, now to show you an example here, we are going to look at a second order system, a mass spring damper system, where the physical system, the mass of it, m, is 1, the damper is 2, and the spring is 4. So your coefficients A2, A1, and A0 are 1, 2, and 4. And we assume that we don't really know them. So although in the system here, but we assume we don't know them. So this is the system here. You can see those gains, A0, A1, and A2, 1, 2, and 4. And for initial condition, both on system and model, we're going to use 0. But it really doesn't matter if this initial condition of the system and the model are different. Still, it is going to converge, right? So here I use 0 and 0, but if you want, I can change them a little bit. So make this 0.1, make this maybe, I don't know, 0.4 or something. So you don't think that the initial condition of them have to be the same. The alphas, the parameters of the model, are different. They are 1, 4, and 4. So the behavior of the model is critically damp. As you can calculate the damping coefficient, you know it's 1 for this system. For this guy here, the damping coefficient is 0.5. So the system behaves underdamped, but your model behaves critically damped. And I want this underdamped system to behave like this critically damped system. To what kind of input? I can decide, either use a harmonic or use a constant. Why did I pick two different ones? To show you that persistently exciting matter still is valid here. If your input has enough of variations in it, then your parameters will also converge to their actual values. If it's just constant without too much variation, the parameters are not going to converge. This is my adaptive control, where beta 0 and beta 1 are selected at 3 and 4. So your characteristic polynomial here, if you go back and look at this characteristic polynomial, remember in this system, n is 2. Okay, in this system, n is 2. It's a second order system. So as I said, this is 3, this is 4, and this is 2. So it's just p1. So you get p squared, and then plus 4p plus 3. And as you know, this is p plus 1 times p plus 3. Both of the roots are negative. And the system is stable, so that is a Horowitz polynomial. Okay? Yep. So going back, what do I need to form my control law? As I said, I need all of these terms. I need to form V. For V, if you look, I need Y dot, and I need Z. For Z, what do I need? I need the error and error dot in this case, and ym highest derivative. Remember, n is 2. So Z in this case is going to be the second derivative of ym minus beta 1 e dot minus beta naught times e. So not only I need the second derivative of ym, in order to find e, I need y and ym. And for e dot, I need ym dot and ym. So I need all of these 5 inputs, ym, y dot, and ym dot, and ym double dot. Once I have them, I can find z, and once I have z, I can find this v. Okay, so I need all 5 of them. That's why if you look here in my Simulink model, the 5 inputs to the systems are the ones I told you. I form my e and e dot, multiply by beta naught and beta 1, add the second derivative, and I form my z signal here. Yes, so the signal is z. Let's see if I can move it. Yes, that's my z signal. And then this z has to be multiplied by what? If you remember in the control, if you look at u is what? U is v transpose times a hat. So I need to form a hat matrix or vector and pre-multiplied by v transpose. In order to find a hat, I need to, as I said, what? Integrate a hat dot. Now, how do I find a hat dot? Go back to equation 12. The terms you need is this constant negative gamma matrix, the v, and then b, and then p and x. And x is what in this case, based on the definition that we have for x? X is clearly, as you can see, is all the way to n minus 1th derivative of e. So it's going to be e and e dot. That's all it is in this case. That's e and e dot. So I need that one for x. E and e dot are already formed when I wanted to what? When I wanted to form my z. So I have them. That means I have x. B is this format, so in this case it's just going to be a 0 and a 1 because the system is order 2. V here, remember the definition of V, you need Z, and in this case y dot and y, right? So it's going to be Z, y dot, and y. Transpose of that is V. And remember we have y and y dot, we already formed Z, so we can get V. P, everything is known. The only thing we need to solve for is P. And for P, I need this equation 13. And remember, P is positive, definite, symmetric matrix. So I can write it as P11, P12, P12, and P22. These two elements are the same because it's symmetric. Now, if you multiply it by A, what is A in this case? A is this format. And remember, it's going to be a 2 by 2, so it's just going to be 0, 1, and then literally negative beta 0 and negative beta 1. That's all it is. So my A matrix, in this case, it's going to be a 0 and a 1. And then remember, beta 3 was 3, beta 1 was 4. So negative 3, negative 4. Okay, and for Q, it's under your control. In this case, I pick Q to be the identity matrix, as long as it's symmetric, positive, definite. So I'm gonna pick this. And now I'm going to solve for what? For the equation 13. And you can do it in MATLAB, you can do it by hand. So here, say A equals, and 0 and 1, then negative 3 and negative 4, as we said. And then we go for P, so we say sims, P11, P12, P22. Then define P to be the matrix of these. And then we say what? We say, as I said, PA plus A transpose P. So P times A plus A transpose times P equals negative Q, which is 1, 0, 0, 1. And since this is symbolic equation, you have to use double equal sign. And if you do that, you get these equations. So I go ahead and bring them into Microsoft OneNote so we can see them. This is what I have. Let me make it a little bit bigger. So there we go. These are my equations. And let's go ahead and separate them a little bit so we can see them better. Okay, now if you solve here from this first one, clearly you can see that P12 is going to be 1 over 6. And then if you plug it right here, you can solve for P22. And if you solve for it, you can see that P22 is also 1 over 6. And once you plug them both here and here and solve for P11, you can see that P11 is going to be 7 over 6. So your P matrix is going to be 7 over 6, 1 over 6, 1 over 6, 1 over 6. That is your P matrix. Okay? And now, just wondering if the liap command is giving me what I want. Remember, liap is x equal liap of A and Q. So let's go ahead and do it. X equals liap of A and Q. And Q, remember, is I of 2 and 2. And if you look at this, clearly that's different from the P that I solved for. These guys are not 1 over 6. And this is not 7 over 6. So my recommendation is be careful. The liap command is not going to give you what you want for this case. Okay, once I have everything, as I said, I'm ready to implement. So this is my negative lambda matrix. And for lambdas, I chose big numbers, 4D. Now, one thing to pay attention about lambda, everything here is a 2 by 2, 2 by 1, 1 by 2. The only thing that is not is lambda. The dimension of lambda is n plus 1 by n plus 1. Why? Because you have n plus 1 a's to estimate, not just n. Remember, you have from a naught all the way to an. You have n plus 1 coefficients in the system. So everything is n by n here. This guy is n plus 1 by n plus 1. And this v vector also is actually, if you look at the definition of v, V is, in this case, a 3 by 1. Okay? Yes? So the rest of it is fine. And if I want to just show you dimensionally that this equation is right, because you might say, hey, this equation does not look dimensionally right to me, I can show you that it is the case, actually. In this case, your x is a 2 by 1, p is 2 by 2. B, remember, is 2 by 1, but transpose of that is going to be 1 by 2. This V is 3 by 1, and this guy is 3 by 3. So this guy has to be a 3 by 1, and you see if you multiply all of this, the dimensions are all working. So if I go here, that's my negative lambda. Then this negative lambda here has to be what? It has to be pre-multiplied by the v, and remember v was z, y, and y dot. So this is how I form v. Look, the first element is z, the second element is y dot, and the third element is y. Okay, so if I go back and show you, you see, that is your v over here. So that is my v. Once I get v and lambda, then I multiply, and look, the way I multiply is k times u. So my gain matrix is pre-multiplied by the signal v. Then what? Then this next portion here that you need to multiply is b transpose p, which is constant. But b transpose p has to be post-multiplied by negative gamma v. Okay, so that's what I have here. Look, the product instead of k times u is u times k. So you can pick that. What kind of format do you want? So I said this matrix is post-multiplied, and this is that b here, and this is what? This is your p, right? So that's p, this is b transpose. Good. The last term I need to form is x, and remember x in this case was e and e dot. So here, that is my e, this is my e dot. I get these two, and I form x, bring them in, and here, since x is a signal, and this a negative lambda vb transpose p is a signal, I need to multiply two signals, and none of them is constant. So I use the multiplication block, which is the product, called product. But this product, not only you can do element-wise, if you want, you can do what? You can do matrix multiplication. So here you have to do matrix multiplication. And the one on the top is the left side, the one on the bottom is the right side. So all of that term goes to the left, x goes to the right. So now this is a hat dot. I integrate it, I get a hat. And what are the initial conditions for a's? If you look, 0.5, 1, and 3, which are clearly different than what? Than 1, 2, and 4. Remember, my parameters are 1, 2, and 4. But here, I assume that I don't know them, so I use 0.1, 0.5, 1, and 3. So you see, I'm not starting at the right parameters. Once I get a hat, I send them to workspace, to outside the block, so I can monitor them. Also, once I have this a hat, you see, I get these individual components of a hat and multiply them by their corresponding components. What are they? Remember, my control law is what? My control law is a 2 hat times z plus a 1 hat times y plus a 0 hat times y. And that is exactly what I did. A 2 hat here is taken to be multiplied by what? By z. A 1 hat is taken to be multiplied by y dot, and a 0 hat here is taken to be multiplied by y. And when I add these 3 signals, that is the u that goes to my mass spring damper system, and that is exactly what I did here. Took it, send it to the system. So I guess I explained everything for you. All I need to is to run this and see whether the system converges to 0 tracking error. If you click, you see it absolutely does. And here error is formed by y minus ym. Okay, look here. Perfectly converges to what? 0 tracking error. What about the parameters of the system? Let's double click and check what we got. Okay, so here take a look. Remember, we started at 0.5, 1, and 3, and I should converge to 1, 2, and 4. If you look at the blue one, a 1 hat, it absolutely converges to 2, although I started at 1. If you look at the red one, a 0 hat started at 3, should converge to 4, but it doesn't. It converges to around 3.6. And this one, I started at 0.5, should converge to 1, but it is converging to about 0.8. Okay? So I get one of my parameters to exactly converge, 2 of them to get closer, but not exactly. Why? Because this signal, this system is more complicated, and one simple harmonic for a second order system is not sufficient. So you need to make this signal more complicated in order for all 3 parameters to converge. But if I switch to a constant block and run it again, you should not expect any of these these parameters to converge anywhere close. You still get 0 tracking error though. That is the important part. You still will get 0 tracking error. Look, you see, perfectly working. But if you look at here, this time the red one is actually getting close, but not exactly. The blue one doesn't go to 2, and the yellow one doesn't go to 1. It passes 1 and goes to like 1.356 or something. So none of them will exactly converge. Even the red one kind of converges actually, but not exactly. So if you want better convergence, you better what? Add more complexity to the R signal to get what? To get your parameters to converge. Here, to show you what more complex signal is, I combine 2 harmonics and send it in. And these 2 harmonics have different frequencies. They are both amplitude 1, phase 1 by a phase 0 by a 0, and frequency of the first one is 1, so it's like sine of t. But this one, if you look at it, frequency of this guy is 2, so this is sine of 2t. So my signal is sine t plus sine 2t. It has 2 harmonics in it. And if I send this in, look, not only error goes to 0, but look at here. You see, the red one goes almost to 4, almost perfect. The blue one almost goes perfectly to 2, and look at the yellow one, almost perfectly goes to 1. You see, I get all 3 parameters to converge because my signal had 2 harmonics in it, not just 1. And if you wondered whether y and ym are the same, of course they should be, because E is your error. So look at here. Let's look at these 2 as well. clearly your desired signal is two harmonics. So you see basically these kind of shape. And if you look here, Ym is the output of the model, Y is the output of the system. And although, look, initial conditions are completely different, but it takes a little bit time for the error to what completely goes to zero. And now you see they are here on the top of each other. So my system can easily track what a very complicated signal, and I can add more harmonics to it or so on. But the good thing is I got all three parameters to converge as well. So now you can do it for any linear higher order system as long as you follow what we had in this lecture, and I'll give you this file to download and to play with and learn from it. Hopefully it was useful to you. I'll see you in the next video. Thank you.